Now, where previously I had depicted the column space, the space of all the vectors you get from the vector, from vectors in R3, I depicted the column space by an axis, one-dimensional, and the null space by an axis, and simply said, okay, these are actually, in general, higher dimensional. They're not just one-dimensional, but that picture clearly shows the idea of the projection of B into the space C, parallel to the space, the projection line parallel or within the null space of AT. This is not really any more realistic, but it's maybe a little more general. Now I'm depicting C by a rectangle and null space of A transposed by a rectangle, and having drawn them where there are right angles here, so that kind of suggests, it doesn't really depict anything, it suggests the fact that these are at right angles as they are. So that's the reason these rectangles are drawn like this. This rectangle actually represents a three-dimensional space in the example that we're talking about. You know, you got to think of this as being a three-dimensional space, and R5 as being a five-dimensional space. You can't visualize a five-dimensional space. We perceive things in three dimensions. We can't perceive things in higher dimensions. We can kind of represent them, but this is the best we're going to do here. And since we can have any number of dimensions, if we had 12 data points, we could observe 12 data points in our depth versus time. This would be R12, okay? You can't visualize it. Okay, anyhow, here's the picture. Now, we know that B, which is the set of our y values, the vector consisting of our y values, is almost certainly not in our column space. Not with real world data, things don't work out that well. So B is out here someplace. And we know, we've developed the idea that the matrix A gives us a row space of A transpose, the null space of A transpose, and that any vector in this space is a unique sum of a vector from the column space or the row space of A transpose, or this column space of A, row space of A transpose. Again, any vector in the space is a unique sum of some vector here and some vector here. A vector in the column space, a vector in the null space of A transpose. So B is uniquely a B sub row plus a B sub n. B sub row here, B sub n here. By unique, that means there's only one B sub row and only one B sub n that can be added together and give you this specific vector B that corresponds to our data, remember. So there's a unique B row in our column space, and that's the vector that's as close as possible within this whole space to the B vector. So haven't written that out before, and I kind of like that statement. B row is the closest vector in W to B. Because since B equals B row plus Bn, B row is the orthogonal projection of B onto the column space. It's the orthogonal projection because it's connected to the B vector by a vector in the null space, and the null space is orthogonal to the column space. Now that's a lot to digest and a lot to sort out, but it's worth thinking about, worth understanding. The textbook will say the same things in somewhat different words and without the gestures and the distraction of me. Okay? So look there too. They're telling you exactly the same thing. It then follows that B row is the vector to which the matrix A transforms X the vector that this transformation maps from x to the b row vector. So the b row vector is your ax. So b row is the closest ax vector to b. It's the vector that we're looking for, and x is its preimage. We find that preimage, as before, by the fact that if we do ax minus b, this vector minus b gives you, well, it'd be the negative of this bn vector, but that's still in the null space, right? If bn's in the null space, the negative of bn is in the null space, and that should be pretty obvious. Okay? So, once we have that, we have all the rest of this, and we've already talked about this. This leads to this equation, this matrix equation that's just equivalent to a vector equation that we can solve, a system of equations that we can easily solve for the x vector. The x vector is our values of a, b, and c. The three components of x are the values of a, b, and c that give us our best fit model for our data.